Welcome back to our discussion of infinite series. Today we're going to discuss one of the most powerful and often used tests for series convergence. It's called the ratio test, and we're also, toward the end of this video, going to discuss a related test called the root test. Before we get started, I'd like to ask you a couple of questions. I'd like you to consider as a warm-up exercise the following three series, and like to ask you to pause the video for a moment and see if you can decide which of these three series converge. And while you're considering it, let's not just consider if it converges, let's consider if it converges, and if so, does it do so absolutely? So if you would pause your video for just a moment, please, and consider these, and then whenever you're finished, please come back and we'll discuss them a little bit. Okay, so let's talk about these. This first series, let's see. So clearly this is an alternating series, and I think it's also pretty clear that if we looked at the limit of if we looked at the individual terms of the series, let's look at them without the signs. So without the signs, the nth term looks like 1 over the square root of n. Well, certainly as n gets larger, these terms decrease in value. And in fact, they decrease to 0. So if we looked at the limit of these terms, we're going to get to 0. Well, those two criteria are exactly the criteria which tell us that an alternating series converges, right? So the terms of the series alternate. The terms decrease in value. If we ignore the sign, they decrease in value as n increases, and they decrease to 0. So sure enough, this series does converge. Does it converge absolutely? Well, if I considered just the positive terms, so the absolute values of the terms of this series are the terms 1 over the square root of n. This is a p series with with p less than 1, right? So we know that p series with p less than 1 diverge. So while this series does converge, it fails to converge absolutely. Let's jump over to series C here. And well, let's see. First thing you might notice is that it also is an alternating series. The signs alternate between positive and negative values. But if you stare at it for just a moment, you might also notice that, well, I'm going to write this first term as a fraction, specifically as a fraction, like all the other ones are listed, so that we can analyze this perhaps a little bit more clearly. If I look at the numerators, looks like my numerators are being multiplied by 3 for each with each successive term of the series. Looks like my denominators are being multiplied by 4 for each successive, if I'm ignoring the signs. And so all in all, it looks like each of my terms is coming from my previous term by multiplying by, let's see, the signs are alternating, so by negative 3/4. And sure enough, that's exactly what's happening. So series C is geometric, and the ratio, right? The ratio is well, it's between -1 and 1, right? Because the ratio is exactly what did we say? Negative 3/4. right? So that falls in that interval between -1 and 1, and we know all geometric series for which the ratio lies between -1 and 1 converges. Even more than that, if we looked at the absolute values of the terms of this series, right? So 5 plus 15 fourths plus 45 sixteenths plus 135 over 64. Well, the ratio, instead of being -3/4, would be 3/4. Well, that still is going to clearly fall within the range from -1 to 1. In fact, it's kind of clear from this example that if we have a geometric series for which the ratio lies between -1 and 1, the absolute values of the terms is going to give us another series for which the ratio lies between -1 and 1, right? It's just going to be the opposite value of the ratio that we had before if the original ratio was negative. And so any series which is geometric is going to turn out to be absolutely convergent if it's convergent in the first place. Series B is a little trickier. Let's just look at the first several terms of this series. I'm going to ignore the fact that it's alternating for just a moment. We'll worry about that later, but for now, let's just look at the terms n squared over 2 to the n, and we'll write out the first several of these. Let's see, whenever n is 1, this is 1 squared over, let's see, 2 to the first. Next term is going to be 2 squared over 2 to the second. Next one's going to be 3 squared over 2 to the third, 4 squared over 2 to the fourth, and so on. And if we looked at the specific values, this is 1/2. This is, 1. This is, what is this, 9/8, a little bit bigger than 1. But then this one is, this is 16. Oh, well, we're back to 1 again, 16 sixteenths. Let's go one more, 5 squared over 2 to the fifth. Well, now we're at, let's see, 5 squared is 25, 2 to the fifth is 32. That number's less than 1. And in fact, if we take successive terms beyond this, 6 squared over 2 to the sixth, let's see, I'm going to be, let's see, so this term is changing by a little more than, well, let's see, I just increased 5 by 1 and squared it. But down here, I'm actually multiplying by 2. That's going to give me, let's see, what do I get here? 36 over 64. You see what's happening? So these terms are, from this point forward, it looks like from this point forward, I have a decreasing sequence of terms, right? So it looks like these guys are decreasing in value, not from the very beginning, but eventually. Right, so they're eventually decreasing. Right, by the time we get to here, from this point on, my terms are all decreasing, and that's good enough. So what I have is an alternating series, and the terms of the alternating series are decreasing in value after the third term. It doesn't really matter, so long as that's happening at some point and continuing forever thereafter. That's good enough for the alternating series test. And in fact, it looks like they are decreasing to 0. And in fact, that is correct. That's exactly what's happening. And so we've got all the conditions necessary for the convergence of a series whenever the series is alternating. And so this one does converge. However, does it converge? Absolutely. And that's going to be the question throughout this particular discussion for a good while, is how can we make that determination? Well, let's ask first, how close the series that I get by ignoring the signs of the terms, how close is this to being a geometric series? I think it's clear to us that it's not geometric. I mean, after all, if we took 16 over 16 and divided 9/8 into it, well, let's see, 1 divided by 9/8 is 8/9. That's not the same thing we get if we take 25/32 and divide 16/16 in it by it. In fact, then we're going to get 25/32 if I take this divided by that, which is not the same as 8/9. I'm going to get something different still if I take this divided by that, right? So I'm not getting the same ratio every time whenever I divide a term by the successive term or into the successive term. So it's not geometric, but is it close to being geometric? And what do I mean by that? Well, all right, so I've written out the first several terms here of this series. Right, so this is what the n plus first partial sum that I have written down here. Let's just look at some of these ratios. So if I took, let's say, 10 to the second over 2 to the 10th and divided it by the previous term, that would be 9 to the second over 2 to the 9th. What I get is, well, let's see, whenever I divide by a fraction, invert and multiply, I get, well, let's see, I have a 2 to the 9th in my numerator here, a 2 to the 10th here. So I'm going to have all these 2's are going to go away together with the exception of 1 left in the denominator. And then I can write 10 squared over 9 squared as 10/9 quantity squared, right? And so what I get is, well, this number right here. Whenever I look at the 100th term and divide the 99th term into it, I get something similar, right? Again, I'm going to get, so I'm going to have a 2 left in my denominator, and 100 squared over 99 squared can be written as 100 over 99 quantity squared. Do you see what's happening, right? So we have a half times something pretty close to 1 squared. Here's a half times something even closer to 1 squared. Let's see. So again, we're asking how close is this to being geometric? Well, it looks like if I look at the n plus first term divided by the nth term, what I'm getting is 1/2 times something really close to 1 quantity squared. And the bigger n is, the closer this parenthesized expression is to the number 1. Right? So again, I'm looking at ratios of terms, and I always get something different, but I'm getting things that are really, really close to, well, it looks like really, really close to 1/2 times something near 1. It looks like I'm getting something very close to 1/2. And in fact, for large values of n, this ratio is in fact near to, well, we did this much already. And as we said, it's 1/2 times something really, really close to 1 quantity squared. In fact, in the limit, this number is 1 in parentheses here. And so in the limit, this ratio is equal to 1/2. And so for large values of n, what this says is that while a sub n over, or a sub n plus 1 over a sub n isn't ever equal to 1/2, it's approximately equal to 1/2 for large values of n. And so for large values of n, the n plus first term is almost exactly equal to 1/2 times the nth term. Now think about this for just a moment. If that approximately equal symbol were actually equality, this series would be geometric. It would be geometric, and the ratio would be between -1 and 1, right? The ratio would be 1/2. It's not geometric, and we don't have equality, but it turns out that this approximately equal to, it turns out that that's actually good enough, right? It turns out that let's restate the geometric series test for just a moment. Geometric series test could be worded like this, right? Suppose that the ratios of a term to its predecessor, suppose that it's exactly equal to the same number for all n. If that number is between -1 and 1, then the series converges. Simple as that. We also know that it diverges otherwise. The test we're introducing today, the test called the ratio test, says almost exactly the same thing. The main difference is, instead of equality here, I'm going to have approximate equality. So suppose that whenever I divide a term by its predecessor, what I get is really close, approximately equal to R for all n sufficiently large. Now, it doesn't really matter what happens early on in the series, but what we're saying is eventually, right, we'll get far enough into the series so that this is true. And by this is another way of saying, suppose that the limit as n approaches infinity of a sub n plus 1 over a sub n is some number r. All right, so suppose that my ratios are approximately r for all n sufficiently large. In other words, suppose that the limit of the ratios of the terms exists. I'm calling that limit r. If r is between -1 and 1, then this series converges absolutely. We could have actually said that up here as well, right? We noted that whenever we did the example on the other page. We could have written absolutely here, right? Because we could have instead ignored the signs of the terms, and if the ratio had been negative before, then ignoring the signs is going to make it positive, but it's going to be the same. The absolute value of that r value is also going to be between -1 and 1. So I could make this down here as well. One difference between the geometric series test and the ratio test is it's not quite as crisp. I do know that if r is between -1 and 1, the series will converge absolutely. But with the geometric series test, if it were anything else, then the series diverged. With this one, turns out we don't know what happens whenever r is equal to 1. However, if r is less than, if it's strictly less than -1, then we are going to have a divergent series. And if it's strictly greater than 1, we're also going to have a divergent series, right? So the ratio test looks very, very similar to the geometric series test. It's just that we're using approximate equal instead of equality for the ratios. Let me neaten this up just a little bit. So suppose we have a series and the limit of the absolute values of the n plus first term to the nth term, suppose that limit exists and is equal to some r. If, since we've taken the absolute values of the terms, we don't really have to worry about the negative values anymore. If all, right, the limit's going to be non-negative. But if that ratio is less than 1, then we have that the series converges absolutely. And if the ratio is bigger than 1, then we're going to have this, that the series diverges. Now, we said just a moment ago that if it equals 1, we're not going to be sure what happens, and I'm indicating that here just to be perfectly clear. If that ratio, right, if this limit is actually equal to 1, we don't know anything about the series. We don't know if it converges. We don't know if it diverges. And we'll see an example of that in a little while later. We'll see an example of a couple of series, one which, or both of which have limits of these ratios of consecutive terms being 1, and one of those series converging, the other diverging, right? So turns out that we don't know anything at all in that case. Why does this work, right? Why should we be able to replace equality with almost equality and still have basically the same conclusion that we had for the geometric series test? Well, let's go ahead and return to the series that was in question here just a moment ago. Right, I'm ignoring the signs for now because, well, after all, I'm going to be looking at the absolute values of the terms anyway, so I might as well just go ahead and ignore the signs. And let's see, we've already noted a few things. So clearly our nth term is n squared over 2 to the n. Right? That's exactly what we're looking at here whenever we examine this series. And so the next term, the n plus first term, well, so if this is what the nth term looks like, the n plus first term is going to look the same, except I'm going to replace n with n plus 1 each time. And so the limit of the absolute value of the n plus first term to the absolute value of the nth term, we saw that that was equal to a half for this particular series, right? And so let's draw a picture here. So what's that saying? Well, so here's a half. And this statement right here says that these ratios, a sub n plus 1 divided by a sub n, they're all pretty darn close to 1/2 whenever n is a big number. I don't know how big, but whenever n is large, there's going to be, we can get n large enough so that these terms are all as close to 1/2 as possible. In fact, what I want to do, this is kind of important. It's actually very important. I want to make sure that I fit all these guys for large n's inside an interval that is small enough to not contain the number 1. Right, so I want there to be some number k out here that's less than 1, so that all these guys, right, they all live in this interval. So they all live here for large n. You know, and just to be specific, let's say that large for our purposes is maybe n being greater than or equal to, how about, I don't know, I'm just pulling this out of the air, 108. All right, so let's say whenever n is 108, I can fit all of these ratios inside of this interval right here. Right, and so what that says is that when n is bigger than or equal to 108, then a sub n plus 1 over a sub n, the absolute values of those terms, is smaller than k. So what? Well, draw this picture again up here. So since all of these ratios are smaller than k, right? So we're assuming n is bigger than or equal to 108. So that means that, so the 109th term divided by the 108th term, that'd be smaller than k. Well, another way of stating that is that the 109th term is, well, I'm just multiplying here by a sub 108 on both sides. So the 109th term is going to be less than k times the 108th term. Okay, fine. It also says that the 110th term is divided by the 109th term is less than k, right? 109 is bigger than n, right? For all n's bigger than 108, we are saying that this is true. 109 is bigger than 108, and so this ratio is going to be less than k. So a little algebra tells us that the 110th term is less than k times the 109th term. But the 109th term was less than k times the 108th term. So I got this k times, well, instead of 109, let's replace that with k times a times, k times the 108th term. So in total, I have that the 110th term is less than k squared, right? That's k squared times the 108th term, right? Let's go one step further, right? So the 110 is bigger than 108, and so I have this ratio less than k. Little algebra tells me that the 111th term is less than k times the 110th term, but here's this k. 110, the 110th term is less than k squared times the 108th term, right? So this is less than that, and so this term in total is less than this term in total. You see what's happening? Right, so if I did this one step further, I'm gonna get that the 112th term is less than k to the 4th times the 108th term, and so on, right? So I'm gonna get this pattern going, and so here I've written the first 110 terms of my series up here. By this analysis that I did above, this is going to be smaller than, let's see, I'll list the first 108 terms again, but then let's see, the 109th term was smaller than k times the 108th term. The 110th term was less than k squared times the 108th term, and so on. But if I start at the 108th term, right, and keep going, of this second series down here, what I get is a geometric series, right? If I take any of these terms and divide it by the previous one, I get exactly the number k. So starting here, this series is geometric. This series that I'm interested in, the one in question, is smaller than this geometric series. Well, since this series is geometric with ratio less than 1, and since this series is smaller still, the direct comparison test tells me that the series I'm interested in converges, right? I'm comparing the series I'm interested in to this series which is eventually geometric, and series which are eventually geometric converge. And since I'm looking at the absolute values of all the terms, all the terms I'm looking at are positive, that meets all the criteria for the direct comparison test and tells me that since I have a series that is less than a convergent series where all the terms are positive, my original series converges. So, since this series with absolute value terms converges, well, that says that my very original series, the one that might have had some negative signs in there in the terms, it must converge absolutely. That's by definition, right? If a series converges, if the absolute values of the terms of a series converge, then the series itself converges and by definition converges absolutely. Suppose on the other hand that, what if I looked at the limits of those ratios and what I got was actually something bigger than 1? Right, we had gotten 1/2 whenever we analyzed the series before. It was something less than 1. But what if those ratios had a limit that was bigger than 1? Well, we could have drawn a similar picture, right? Except what we would have had is that these ratios would have lived in some interval strictly bigger than 1 for large enough n, right? I don't know how far out I'm going to have to go, but I can, if this is true, right? If my limit is bigger than 1, then eventually these ratios are going to be bigger, right? So this is my number r right here, and so since r is bigger than 1, I can choose an interval again that doesn't have 1 in it. So again, I'm going to be able to find some k that's bigger than 1 for which each one of these ratios is bigger than that number k. Right? Well, this is going to be very similar to the argument I gave before. Just going to kind of work in reverse. Since these ratios are bigger than k, the n plus first term is going to be bigger than k times an for every one of those numbers that were big enough, right? That's what we were using 108 for capital N before. I don't know what n's going to be, right? I made 108 up before. And so if I write down the terms of my series, those are going to be bigger than, so I'm going to write down the terms of my series again up to a sub n, but then I'm going to note that, let's see, so by the time I got to big enough here, a sub n plus 1, that's going to be bigger than k times the previous term. But then as I move forward, I'm going to be able to write my a sub n, this should be a capital N, n plus 2, as being bigger than k squared times a sub n, and so on, right? And since k is bigger than 1, starting here, I do have a geometric series, but I have a geometric series for which k is bigger than 1, so this series diverges. This series is bigger still. So again, by the direct comparison test, this series of absolute value terms is going to diverge. But even worse, right? If I looked at the, so I'm looking at, we got a sub n, we got a sub n plus 1, we got a sub n plus 2. If I look at these a sub n plus i's as I heads toward infinity, so I'm looking at larger and larger ones of these, what this argument shows is that it's bigger than or equal to, let's see, this would be a sub n times k to the I, n plus 2 here, k to the second. So I'm looking at this term being bigger than a sub n times k squared. One after that's going to be bigger than a sub n times k cubed, and so on. That is going to run to infinity. Well, then clearly the limit of these guys, right, the limit of these terms, if it's running off to infinity, it's certainly not equal to 0. And so it doesn't even pass our prayer of convergence test, right? So what we're saying is that if it turns out that this limit of ratios is bigger than 1, then we have necessarily that the series in question diverges, right? Finally, what would have happened? So we've looked at what happens whenever this is bigger than 1, right? We're going to get a divergent series. We've looked at what happens if this thing is less than 1. We get a convergent series. What happens if the limit of these ratios is equal to 1? Well, we stated earlier that we know nothing, but let's see if we can actually show why that's the case, right? I'm going to draw a similar picture to what we drew before. If that limit of these ratios is equal to 1, then the best we can do is to say that we can choose as small an interval as we like around 1 and insist that we can go far enough out into our series find large n such that these ratios live within that interval. But that doesn't allow me any room to find a k that's bigger than 1 or a k that's smaller than 1 in order to make the argument that I made before, right? Whenever r was smaller than 1, I could find a k that was bigger than everything in the interval. Whenever r was bigger than 1, I could find a k that was larger than 1, but less than all of the numbers in that interval. Here, I don't have that luxury, right? So whenever the limit is equal to 1, I'm not able to use either one of the other two arguments to draw a conclusion. And in fact, no matter how hard I try to find an argument, I'm going to fail because, well, I can actually find examples for which the limit is equal to 1, limit of these ratios is equal to 1, some of which come from a series which converges and others which come from series which diverge. And here's the classic example. Let's consider this p series with p equal 2. I know this converges, right? I know that converges. But if I looked at the n plus first term to the nth term, what I get is a ratio that converges to 1, right? So I'm in this situation right here. So I have a ratio that converges to 1 for a convergent series. However, if I looked at the harmonic series, the p series with p equal 1, these ratios also have a limit of 1, right? So I'm in this situation. But this series diverges, right? So I can have my limits go to 1 sometimes with a series which diverges, sometimes with a series which converges, which tells me that simply knowing that the limit is equal to 1, that tells us nothing about the series, nothing at all. We can draw no conclusions whatsoever. All right, I want to do one more example. And this example isn't going to have anything at all to do with the ratio test. This is going to introduce a new test. My example is this. Now, what I notice, all right, so the nth term obviously is, well, the absolute value of the nth term would be the absolute value of what I'm looking at here. And so notice that if I looked at the nth root of this term, right? So if I took the nth root of this, well, the nth root of this is just going to be sine n over n, absolute value of sine n over n. I also notice that the limit as n approaches infinity of this nth root is equal to 0. All right, so what? Well, the root test, which I'm going to state in just a moment here for you, is going to tell me that this series, that this original series converges. Well, here, let me tell you what the root test is exactly. I'm going to bring back the ratio test for you. And it turns out that the test that we just described is almost exactly identical to the ratio test. Let's change it. Instead of ratio, I'm going to write root. All right, so the root test says we're going to let R be, well, instead of the limit of ratios, we're going to let it be the limit of the nth root of the terms. Everything else is absolutely identical. So the root test says that if I look at the limit of the nth roots of my terms, I call that R, if that limit is less than 1, my series converges absolutely. If it's bigger than 1, it diverges. If it's equal to 1, we know nothing. Let's go back to that example again. Right, so in this example, there was my nth term. there was the nth root of my nth term, right? What we're saying is that if the limit of the nth roots are less than 1, the series converges. Well, the limit of the nth root was certainly less than 1. In fact, it was 0. And so the root test says the series converges. Done. Simple as that. Why does this work? Well, it turns out that the reason that this works is very similar to the reason that the ratio test works. Let's go ahead and let R be the limit of the nth root of the nth term, right? And so what's that say? So that says that R is approximately equal to the nth root of the nth term for large n's. Well, another way of saying that is that R to the n is approximately equal to a sub n for large n's. Let's draw a picture similar to what we had before, right? So this limit being equal to R, and let's, well, we had R being less than 1 up here. Whenever that happens, we can, since R is less than 1, I can find an interval that doesn't contain 1, that is going to contain all of the nth roots of a sub n whenever n is for large n's. And so for those large n's, for those large values of n, the nth roots are going to be smaller than some number k, where k is strictly less than 1. Again, R being smaller than 1 allowed me to choose a small enough interval around R so that 1 didn't belong to it. Right, so we have that the nth roots are less than this k, which means that the terms themselves, the absolute values of the terms themselves must be less than k to the n. Right, I just took the nth power of each of these numbers. Whenever I take the nth power of this, I'm just going to get a sub n. Take the nth power of this, I'm going to get k to the n. And so if I wrote down the terms of my original series, those are going to be smaller than, let's see, I'm going to write down the first bunch of terms, but whenever I get large enough, and I was using 108 before for large n's, all right, so I don't know what the number's going to be. There's going to be some place at which I can start saying that a sub n is less than k to the n. So a sub this position, a sub capital N, is going to be smaller than k to the capital N. A to the n plus 1 is going to be less than k to the n plus 1, and so on. But starting here, this is a geometric series. Since k was less than 1, it's a convergent geometric series. And this series has terms that are smaller still. So again, by the direct comparison test, since this series converges and this series has terms that are smaller still, and all the terms are positive, the direct comparison test tells me that my original series converges. And that is an explanation of the root test and why it works. It looked very similar to the ratio test and why it worked. Turns out that the ratio test is, in fact, one of the most useful tests that we're going to be employing going forward. And so you're going to want to be very adept at being able to use it. That's all for today. I look forward to seeing you again next time. Stay healthy. Take care.